Here we're starting the second recording or new recording, but theoretically you've already watched at least one of those brutally long videos that goes through all the gory details. What we're seeing here is part of the summary, spectSum.tc file, so the big kind of key aspects behind this. Just to give you a quick labeling behind this, we're looking at our IR spectroscopy here. We're looking at our NMR over here, in particular HNMR up top and then CNMR down below, and then we have our mass spec kind of summary right there. So this covers all the big pieces behind it, which now sets us up to do the next and exciting thing, which is start solving. I'll give you 30 seconds. Whoops, I lied, not quite yet, gave it away too much. This is our spect organization document. You'll notice that we've got lines for each of the forms of spectroscopy and little places where we can try and put information. All we're trying to do is, again, organize our information and our process so that when we solve a bit of information, we don't undo that by keeping it in our head. Because you keep it in your head, you're going to lose track of it. Write it down so that you have it so that you can manipulate it and work with it later. You also need to keep it organized because you'll probably be adjusting structures as you move. If you can follow a sequential system, that can improve your success. Okay, I would hearken this to puzzles. We're putting together a puzzle. In the process of doing a puzzle, you don't put two pieces together and then set them aside for somebody to take apart later. You leave them put together so that you can put the next one on. That's what we're doing here. We're writing these pieces down by connecting those things. Once they're connected, we're good to actually move on to the next stage, which then sets us up, hopefully, for your practice. We'll give you 30 seconds. I want you to write down everything that you see within this spectra, and I'll try and be silent. 15 seconds left. We'll go ahead and pop it up with a quiz question on what you got. And now, real quickly, what I would go through and recommend you do. So, I'm seeing an OH. This dotted line, these are under that, so I'm going to see CHSP3 hybridized. 15, 16, 17, I got something, maybe 1650. That's a little bit dodgy. It's a little bit low for me to call that a carbonyl. I'm probably going to stick with it being a carbon-carbon. With there being another sequence or a bunch of sequences there, I'm going to bet that this is a carbon-carbon aromatic. Okay, so it's the combination of those. For those people being like, okay, well now what's the answer? That's it. That's what you should be doing. You've now analyzed it. Those pieces can potentially take you somewhere else. Okay, we might throw in also the carbonyl with a question mark, but again, we aren't 100% sure. Don't worry about it. This whole region is dodgy to analyze. Okay, I would go almost as high as that 1600 range to be dodgy to analyze because it's easy to overanalyze it and say there's 500 million different things in there. It's the fingerprint region. Stay out of it if you can. Okay. With that, we can go ahead and say, cool, good job. Move on to the next one. I'll give you another 30 seconds. See what you can come up with. Ten seconds left. Give me some information. Went a little bit over, but we'll go ahead and walk through it again. Again, thinking about the process, this is roughly how fast you should be moving. We're looking for the tallest peak furthest to the right. So we go furthest to the right, depending on how close you want to get. We can see those. The tallest peak within 3 units of that is going to be this guy. That's going to be my M plus peak. That M plus peak is at 1, 2, what is that, 3? Yeah, 93. I know the molecular weight of my compound is 93 grams per mole. Because that is an odd molecular weight, I know nitrogen is present. The next part, if I really wanted to dig into this, actually, before I do that, I'll take a look at the 93 and I'll look for a +2. So 93 plus 2 would be 95. Okay, that peak, almost non-existent. So it's not 1-to-1, which means no bromine. It's not 3-to-1, which means no chlorine. The mass is lower than 127, which means no iodine. Okay? So really all we've got is that we've got an odd nitrogen. If that's all you get out of mass spec, that's really good. What I'll probably have on an exam is one more question to see if you can take it a little bit further. Because I know I have at least one nitrogen, what I'm going to do is take that 93 and I'm going to subtract the mass of nitrogen, which is 14. I don't have a periodic table handy, but I think it's 14. 13 minus 4, 9. I wish I had a calculator. 79. Close enough, hopefully. 79. Okay, so I know my formula, because it's an organic chemistry class, has carbon, some unknown amount, hydrogen, some unknown amount, and I'm saying nitrogen with 1. Okay, I don't have any evidence for oxygen, at least in this spectra, so I'm not going to include it in my formula. I know I don't have bromine, chlorine, and iodine, so there's no evidence for any other elements, which means my formula is going to be C0H79N, okay, which would really mean H79N. That makes no sense as a formula, but what I did was just took that entire mass and said it was all hydrogen, because hydrogen weighs 1. That likely isn't true. It probably makes more sense if I go through and take 12 into 79. 6 times 12 is 72. That gets me 7 left over. 12 isn't going to fit in there, so that's going to argue that I have C6H1N1. Okay, I need to account for that remaining 7, assuming I did my math right. How can I account for that? I can say that that is hydrogen, and a potential formula would be C6H7N. Another possibility, what if I only had 5 carbons? Okay, well, that 12 has to go somewhere. The easiest place for that to go would be hydrogen H19N as a potential formula. Another formula thing that pops up that can be useful is a fully saturated alkane, CnH2n plus 2, meaning there's no double bonds, no heteroatoms. Every potential connection I can have is a single bond either to carbon or hydrogen. So that would be the maximum amount of hydrogens. How do we use this? N is 5, 2n, so 2 times 5 plus 2 would get me 12. The most amount of hydrogens I could possibly have would be 12. This formula makes no physical sense. I know this is my formula, okay, assuming I don't have multiple nitrogens, okay, but that would get us to that point. We've now analyzed as much as we can with the mass spec, which is then going to take us on to the next spectra, carbon NMR. Same deal, spend 30 seconds to go through and look at it. I got to go talk to my wife real quickly, so we'll give you that 30 seconds to look, and we'll see what we come up with here in a second. Okay, I believe we are back and live, so how do we go through and interpret this one? Same kind of process. We want to go through it as fast as possible. We want to identify how many peaks. 1, 2, 3, hard to tell, maybe 4, 5, 6, might be 7. So I could go 6 to 7 peaks, which means I have 6 to 7 unique carbons in my structure. Okay? Next part, do I know anything about those individual carbons? Well, this one's nice and low, which is going to suggest that we're looking at alkane type carbons. These ones are all significantly higher and show up in the alkene or aromatic type range. So what does that mean? I've got an alkane, 6 to 7 peaks with unique carbons, or 6 to 7 unique carbons. I've got an alkane part of it, and then I have a bunch of either carbon-carbon double bonds or aromatics as likely results. That's it. That's all we get out of the carbon NMR. Right? So we keep it relatively simple, and that's all we can pull. Last one, HNMR, same deal. We'll give you another 30 seconds. Probably mean because HNMR takes the longest, but tough. This would be where having that spect.org file would really come in handy. So I'm going to try and hand draw it out as best I can so you can get an idea of that process. First and foremost, I see 1, 2, 3, 4 groups of signals. What does this mean? I have 4 unique hydrogens in my structure. The next part of this is I could go through and break down that chemical shift where those fell. So if we looked at chemical shift, that red one, I won't specify the value, but the interpretation, maybe I do want to specify the value. The red one falls in at about 0.9. If I was to interpret that, really simply, I have a hydrogen bound to a carbon. Alkanes, there isn't a whole lot else with it. Same deal with the blue one following in at what, 1.5? Hydrogen bound to carbon. Purple one is starting to get up to a range that is potentially something else, but we're still sitting in that carbon alkane range. And then that last one, orange at 2.5, really all I can say is H question mark. I actually don't know what it's bound to. That chemical shift range is very challenging because lots of things start to fall in there, so I don't want to overinterpret. The next thing I would move into would be the integration. Okay, so the integration is the area underneath the curve. In a real system, you would have that information given to you. Since it's not explicitly given, you're kind of at a loss and we kind of have to make up for it. The make up for it is we're really approximating roughly the areas between those and how they compare out. One of the cheats you can sometimes get away with is just the height of the peaks. So if we go through and take a look, that red one is much higher than the others, so we might go through and call that a 3 hydrogen signal. Right? Well, if that one's a 3 hydrogen, this is probably a 2 hydrogen, and this one's also probably a 2 hydrogen. You might say, well, isn't that lower? Yeah, it's lower, but you have more signals. Okay, that signal split out. So we're talking about the area underneath the curve. The area under that big broad one is a lot larger than the one that's taller than it. So we have to consider that that signal splits into multiple things, and that can affect your area. That purple one, single peak, relatively short, is going to be the lowest of all of these, probably going to represent 1 hydrogen. So if we were to go through with our integrations, we could say 3H, 2H, 1H, 2H. What is our interpretation? Well, an interpretation of this means I have 3 hydrogens. The easiest interpretation is to have all 3 of those hydrogens connected to the same carbon. In the next case, the easiest interpretation is to have them connected to the same carbon. Last case, or purple one, just connected to that 1 hydrogen. And then for that last one, we have 2 hydrogens connected, but what are they connected to? Since I didn't actually come up with that interpretation in the chemical shift, I don't know. I don't know what they're connected to. So I don't have that ability to drop that interpretation in there. Because I'm running out of lateral space, I'm going to backtrack and delete the chemical shift interpretation from this. Okay, so we're still constantly scrolling to the right. I just want to make sure you're aware of that. The next thing that pops up would be multiplicity, which is how many peaks we see. So for the red one, we see 3 peaks. For the blue one, we see 1, 2, 3, 4, 5, 6 peaks. Okay, for those of you having a hard time counting that, that's okay. It comes with practice. You'll pick that up in a little bit. You got to see more spectra to see them. Okay, one of the things that can be challenging with these particular signals is seeing how many peaks you see in there. How many peaks do we have? Come on, draw. There's 2 peaks, right? How many white spaces do we have? So if you can go through and count the white space, the valleys at the bottom, that can also help you identify those peaks, because it should be coming all the way back to the baseline or darn close to it for that. But that gets us our multiplicity. The first layer of interpretation is the neighbors. If I have a multiplicity of 3, that means I have 2 neighbors. N plus 1 equals your number of peaks, so 3 is peaks. Your number of neighbors is going to be peaks minus 1. 5, 0, and 2. Okay, and now I gotta erase the integration information, or at least that raw stuff, and now we can actually get to our final interpretation. And what does this mean? I have neighbors of 2, so for sure the past is true. I still have that interpretation, and I have to have 2 neighbors. Well, here are 2 neighbors. Ta-da! Right? They have to be within the 3 bonds, so cool. One option is now to just continue through and do this interpretation all the way down, which is what's shown in the videos. I also have an option of saying, well, I now know that these hydrogens exist and they have 3 neighbors. Do I have a 2 hydrogen signal that has 3 neighbors? Okay, I don't see any. Okay, so that could just be a dead end, so we could accept that and just go through. I think I may have just undone more than I wanted to, and we could just go through our standard method. Hydrogen, hydrogen, right? 5 neighbors? How do we get 5 neighbors? Well, the easiest way to do that would be to split it up along those lines. Okay? 1 neighbor, don't really have a lot of information. We would just say, or 0 neighbors, it would just be CH. We don't have anything else to add to that. Okay? And then the last one, with 2 neighbors, we have H question mark H. Then with its neighbors being 2 neighbors, we could draw that. That question mark we actually know something about, because now, since we know it's splitting, we know that that has to be a carbon. We now have a bunch of pieces. Being able to put those pieces together, some of that can happen by just looking at the HNMR. Most of it's going to require looking at all of your spectra. We've done our full interpretation all the way up to this point. Now what we do is pull in all the information from all the other spectra for this particular compound to try to get to a structure. But I did pull a sneaky on you. All 4 of these spectra belong to different compounds, so don't start trying to overlap them. Okay? With that, I'm going to go ahead and say we're done. We've done the fast walkthrough on this. You should go back through and practice these and see if you can pick up some of that speed. We did all of those spectra in about 10 minutes. Okay? And that's with showing all that work and writing that down. And we had about 4 minutes in between of just delay time. Okay? So with that, thanks for watching this one. Hopefully that helped. Keep coming back and reflecting on it. You will see these kind of things pop up again. I think I've got at least one more planned to show up through this unit. Okay.